Okay, hello everyone, and I hope that you're all getting on okay. I noticed that some of you are not fulfilling all of your obligations for deliverables. Please make sure that you are working throughout the week. Remember that you are expected to devote about 3 hours of work to this class. That is, whatever I teach will be take up part of that, and then the rest is you doing the exercises and everything. Please do not skip exercises. Please watch every video. It's been carefully chosen for you. Do all the exercises, because this is how you're going to gain a body of knowledge, a working body of knowledge to take away from this class at the end. In particular, please pay attention to the discussion groups. Many people are only submitting their own contribution and not following up with other people. If you do that, you're only going to get partial marks. There are many people in the class who are being really energetic about participating in discussions, commenting on other people's, and they are going to be rewarded for that. Others, you need to really pick up on your contributions to discussions, please. It's really important because we're not meeting face to face. And a lot of this material becomes solidified in your brain when you actually think about it and discuss it and talk about it with other people. And this is your only opportunity. The discussion is your only opportunity to do that. Okay, so today we are going to be discussing the global climate change, one of the most important topics which we are going to cover in this class. And it is a topic which is going to impact very, very solidly on you as the rest of your lives unfold. You are going to see more and more impacts of global climate change. And we need to understand very clearly how it originates. This is a topic which impacts on people's political views, on their religious views, on their lifestyles, on every aspect of our lives will be affected by global climate change. And most of you are going to live to see really profound effects. We are already seeing profound effects, but you're going to live to see really, really profound effects of global climate change. And it behooves us all to understand what is happening and also to make commitments to try to limit the damaging effects of global climate change. So let's try and move through, just understand the science, not the politics, not the religious aspects, not the philosophical aspects. Let's try and understand the science behind global climate change. So climate change, you will have already have learned a lot about climate, how it's established, and how climate actually determines the structure and the function of biomes. And those biomes are established over a very long period of time. We characterize biomes very largely by their vegetation, by their climate structure, and then associate with the biomes are animals, etc., which evolve together with the biomes over a very long period of time. So under ideal conditions, they are really stable. And the climate, if it changes, it usually changes slowly, and organisms can evolve together with the evolving biome structure, climate structure. But in really profound climate change would result in the change in the actual functioning of the biome. So, for example, what if winter in Pennsylvania, which normally looks like this, cold, deciduous trees have all lost their leaves, the ground may be frozen, etc., etc. What if the winter in Pennsylvania begins to look like winter in Florida? What is the impact going to be on vegetation? What is the impact going to be on the associated animals, insects, everything else that are associated? It will be very profound, very profound. What we're looking at is a change in structure and function of these ecosystems because of the change in climate that impacts on them. So studying climate change is really difficult in many ways for different reasons. First of all, climate change can occur over different time periods. So you may have a change in climate which is relatively temporary, maybe over decades, and then return back to its original. It may be over longer periods of time, centennial, that is over hundreds of years, or thousands of years, or even longer. We're going to look and see that, in fact, over a long period of time, the climate on the Earth has changed radically. And several times there have been major changes in the overall climate of the biosphere. And not only that, but climate changes may occur in different areas, in different parts of the world, and it may occur differently in different parts. So it could be, just local changes, but what we are going to be discussing are global changes over the whole biosphere. So in order to discern whether climate change is taking place, here's an example of the temporal difficulties. So here is, this is a video clip from yesterday. I don't know if it's going to work. Let's see. Yes.
California's Governor Gavin Newsom proclaimed a state of emergency for 8 counties in Southern California as
this is the major storm which is currently occurring in California.
Rains, life-threatening floods, damaging winds, and mudslides.
Very slow moving. There's initial indications now that it's stall out Monday and Tuesday near LA County.
40 million people in the state under flood alerts. In Los Angeles County, numerous evacuation warnings, officials creating emergency shelters for people and animals.
The LA River has already started to rage, and this was coming from almost nothing an hour ago. The atmospheric river like a fire hose into Los Angeles for the next 2 days.
In addition to the rain, the Sierra Nevada could see snowfall that will be measured in feet. Evacuation orders issued in Santa Barbara County, where they've already received 300% of their normal rainfall for this time of year. In San Jose, a massive tree falling onto this house and another crashing down on this townhome. ABC's Zareen Shah's in Santa Cruz.
The wave crashing down behind me. This part of the beach is closed off to the public.
The storm bringing down trees and power lines in Sonoma County. In Santa Rosa, a tree falling on this car took rescuers over an hour to free the driver.
That driver sustained major unknown injuries, was transported to a local hospital.
The governor's office has put 21 swift water rescue teams on standby and is readying the California State Guard for rapid deployment. Brian Clark, ABC News, New York.
Okay, so now we've got to actually ask ourselves, that weather event that's taking place in California, is that due to global warming? Well, we cannot say. It's simply impossible to look at a single weather event like that and ascribe it to global warming. But California, over a period of years, has shown an increased number of these kinds of storms. And so it begins to look as if the overall climate of California is changing, and it is most likely due to global climate change. Nonetheless, you can't take a single event like that and say that is because of global warming. But you can look at a pattern over a period of years. You have to decide how many years you're going to look at in order to see if there is a pattern of climate change that we can ascribe to global warming. So let's have get some understanding of how the atmosphere actually functions to maintain the Earth's temperature. So we've already learned that solar radiation impacts on the Earth in 2 forms. two principal forms. The first is visible light, and the second is infrared radiation. Infrared radiation causes heating. So the light which impacts on the globe would be absorbed by the surface, some absorbed by the atmosphere, but most absorbed by the surface and converted to infrared. It is converted to heat, and that heat is re-radiated. Now, a lot of the radiation from the sun is actually directly reflected. We only deal with a small portion of the solar radiation, which makes its way through the atmosphere and impacts on the surface of the Earth. So if there was no atmosphere at all, then all of this radiation would be converted to heat and would be radiated straight out to space and would be lost. But that is not what happened. In actual fact, if that was the case, what we would find would be some areas of the Earth under direct sunlight would be extremely hot, but they would get very, very cold very, very quickly once the sunlight disappeared. But that's not what happens on our planet. Instead, this radiation, which is absorbed by the surface of the Earth, is re-radiated as infrared radiation. And in our atmosphere, there are sets of gases, carbon dioxide, methane, and a few others, which are able to absorb the radiation and re-radiate it back towards the Earth, back to re-warm the Earth. This can happen several times. Every time it happens, of course, this is inefficient. Some is radiated out to space. And ultimately, over a very long period of time, a balance is achieved. And that balance keeps the Earth at an equitable temperature, but not too hot, not too cold. We sometimes refer to the Earth as being the Goldilocks planet. This is very important. This is the principle of greenhouse gases. These gases, which absorb energy that is radiated from the surface of the Earth and re-radiate it, are called the greenhouse gases because they act like a blanket. A greenhouse, by the way, works because light can pass through glass. When it hits the inside of the greenhouse, it is converted to heat and it is re-radiated, but it can't make its way through the glass. That's why a greenhouse warms up. In this case, our greenhouse gases are acting in the same way. They are like a blanket, and they warm the surface of the Earth. And it is thanks to them, in actual fact, thanks to the naturally occurring greenhouse gases, that our Earth is kept at a temperature which is suitable for life. So it is certainly true that there are some areas like north and south which are extremely cold, where life would be extremely difficult. But the rest of the Earth is kept at a temperature where the processes of life can easily occur. So it's thanks to the naturally occurring greenhouse gases that that life actually evolved on our planet. Here's the problem. This balance, the occurrence of these gases in the atmosphere has established a balance over a very long period of time. And it is all dependent on life processes that are taking place in the biosphere as to how much carbon dioxide, etc., there is in the atmosphere. But we, unfortunately, are now adding greenhouse gases. We are increasing the concentration of greenhouse gases in the atmosphere. And that increase of greenhouse gases means that more and more heat, which is radiated from the Earth, is re-radiated back. And that is why global climate change, you'll often hear it referred to as global heating or global warming. The global climate change results from this global warming, results from the additional warming which we are causing by increasing these greenhouse gas concentrations in the atmosphere. So you will often hear people say that we don't have anything to worry about because carbon dioxide and climate have changed radically in the Earth's history. And well, there's nothing wrong with that. So why are we worried about climate change now? Well, there are several answers to that. But in order to answer those questions, we have to actually go and look at previous climates. And that's not necessarily an easy thing to do. But we can, in fact, reconstruct climates very, very far back in the Earth's history. And here are some of the ways in which we do it. The first, a very important set of data can be gathered from looking at tree rings. Now, you probably know that trees lay down 2 rings of bark, of trunk rather, every year. One is laid down during summer, one in the winter. And the one in winter is usually narrower than the one that's laid down in summer when growth is rapid. So these rings actually vary in width, not only depending on the season, but depending also on temperature and the availability of water. So when we look at the width of the tree rings, we can actually work out more or less what the climate was like in those particular seasons. So an individual tree, some of our very oldest trees are thousands of years old. Most trees don't live nearly that long. And oak trees may live for several hundred years in the best instance. But we don't need a very old tree in order to be able to reconstruct climate based on tree rings, because we can actually match up. So here, let's say, here we have a younger tree and it's been cut down. Here are its rings, and you'll see that there is a pattern of rings, a distinctive pattern of rings here. Now we can go to another much older tree, even a dead tree, and we can look at its tree rings, and we can actually match those patterns. But now this tree goes back much further. Now we can establish new patterns, and we can begin to look at other wood. And in order to do so, a scientist who does this is called a dendrochronologist. And a dendrochronologist will use wood from as many different sources as they can, not only in the forest, living trees in the forest, dead trees in the forest, but they can also go to lumber, for example, lumber which has been used in construction to build buildings, and see the patterns which can be matched up. And this is an extraordinary fact that we have a continuous tree ring data set which runs back 4,000 years. That is a very long time. That is almost the length of time of our civilization, from not that long after we started settling into cities and towns. So this is a very, very long data set which gives us very good climate data for how climate may have changed over that period of time. The second data set is very important, but this is a modern data set. This extends back to the 1950s. And it's the Mauna Loa carbon dioxide registration. And what they have done on Mauna Loa volcano in Hawaii is they have been continuously monitoring carbon dioxide concentrations. And this is done continuously. And so we have a record for the 20th century into the 21st century, which is very important because the world has seen such a boom in industrial activity in that time. And we will return to this data set in a while, but I'll just show you very briefly what it looks like. So this is from 1998, relatively recently. And what you see is, you see these peaks and valleys. These are seasonal peaks and valleys. There is a lot more vegetation north of the equator than south, and and it tends to use up carbon dioxide during the summer months and then release during the winter months. So we see a seasonal peak like this, but you can easily draw a line through this. It's not a straight line, it's actually a curve going up like this. And you'll see that since 1998, if we do that, we've gone from about 300, let's just say 370, 368 or something like that, all the way up to about 387, something like that. If this is only to 2009, and I have to tell you that this line carries right on up to about 400. So from here, about 367, something like that, to 400 in that span of time. That is the overall increase in the carbon dioxide levels in our atmosphere. A very, very distinctive increase. And by the way, when I talk about these numbers, it is measured parts per million by volume. So it's parts per million by volume of carbon dioxide in the atmosphere. And this, had we been able to measure carbon dioxide before 1958, we would have found similar increases going back quite a number of decades. So we'll talk about why in a second. The third is probably in many ways the most important for looking at ancient climate. And these are ice cores which are drilled out in the Arctic and Antarctic. The Antarctic ones are by far the most important. And when ice forms in the polar regions, it traps gas and it preserves bubbles of gas, which are the same as they were when the ice was formed. And these ice cores are built up very, very slowly. These ice beds, rather, are built up very, very slowly. So a single ice core can go back very, very far. And scientists can sample the gas in those bubbles and analyze it. And there are two things that they analyze most importantly. The one is carbon dioxide, and the second is oxygen. They look actually at oxygen isotopes, at different molecular forms of oxygen, because these vary with temperature. So those little bubbles give us a measure, first of carbon dioxide levels, and second of all of temperature. A very, very good record, which goes back, the oldest continuous core, believe it or not, goes back 800,000 years, almost 1 million years. And by the way, this is just for your interest. There is a link here to a paper which tells you more about ice coring if you're interested. So this is one of our most important data sets for examining ancient climate. And this is from this very famous core called the Vostok core, which in this case, what we're looking at is we're going back just about 425,000 years ago. And I want to show you something here which becomes increasingly important. And that is that there is this very strong correlation between carbon dioxide levels in the atmosphere and temperature. And that is because carbon dioxide is one of the most important of the greenhouse gases. It does vary in concentration. If you go back to one of our earlier exercises, you know, when you could look at the structure of the Earth over time, that app will actually show you also carbon dioxide and temperature for the ancient climate. You can go and do, I haven't set that as an exercise. You can do that yourself if you want to do that. But here is a very, very clear demonstration. First of all, carbon dioxide levels have indeed changed radically over a periods of time. They do so periodically. That is, you can see here, sometimes they're high, sometimes they're low, then they increase, then they decrease, then they increase, then they decrease. Each of these little curves here denotes an ice age. And the peaks here are interglacial. These are when there were no ice, when the ice was at a minimum. This is when ice is at a maximum. So you see that the ice ages occur with regularity. The reason for that is for you to find out when you do your paleoclimate exercise, you will find out that there's a very amazing planetary system which determines when the ice ages are likely to occur. But as we trace this through for each of these ice ages, what we find is that there's this very strong correlation between carbon dioxide and temperature, which has been repeated over and over and over again. So we now realize that layered onto the natural changes in carbon dioxide concentration are the changes which we are imposing on the atmosphere. We are pumping carbon dioxide into the atmosphere. And this is resulting in a rapid increase in temperature of the biosphere. So let's just think for a minute. Have a look here at the time scale that we're talking about. So this here, that is 50,000 years. So let's look at this increase in temperature here. And what it is, here's the increase in temperature is going to be shown here. It's going up by about 3 degrees or so above the mean, above the normal. And it's doing so that's 3 degrees centigrade. That's a lot. That's a lot. And that is a tremendous amount of heating. But it's doing so over what period? It's doing it over 20,000 years, a long period of time. And that is enough time for organisms to adapt, to shift their range, to adapt to the changes in temperature without mass extinctions occurring, without disaster befalling that particular ecosystem. That is a very important point. These changes here are slow. So when we look at all of that data and we put it together, we find that there's this very strong, it's called a correlation, of course. Here's our concentration of carbon dioxide. Here's the temperature. And you can see that there's a very strong association between the increase in carbon dioxide concentration and increases in temperature. And that's what we've got to pay really careful attention to. So here's why I belabored the point about the time period over which the changes take place. Here are the same. Here are all our ice ages: increase in temperature, decrease, increase, decrease, increase, decrease. Taking over a period of tens of thousands, if not hundreds of thousands of years. And look at the level to which the carbon dioxide rose. About 300 parts per million, the volume, is the maximum that it rose to in these last 450,000 years. Here's our modern period. This is us now. In actual fact, this is a little bit out of date. This would be up at 400 parts per million by volume. That is the modern level of carbon dioxide. And we now have to look at how rapidly this change has taken place. And it has taken place in less than 200 years. As opposed to tens of thousands of years, this massive increase in carbon dioxide levels has taken place in hundreds of years. And that is far too rapid for these living systems, these ecosystems, to adapt. And as one of the results of this that we believe is going to happen is that we are going to see mass extinctions of organisms which are simply unable to adapt to the resulting high temperatures, which are going to, if we carry on as we are going. So here again, this is just another demonstration of it. And you can see, well, let's go 20,000 years ago, there was actually a carbon dioxide minimum, and that increased to about 300 or so, or maybe 275 in 20,000 years. And now we have leapt from there to 400 in less than 100. So this is extremely rapid change, and it has the potential to be disastrous. And the reason for that is very clearly associated with a massive change in the nature of human civilization, which began about 200,000 years ago, 200,000 years ago, 200 years ago. I'm sorry, I'm getting my time scales mixed up. About 200 years ago, of course, the Industrial Revolution began. And the Industrial Revolution was funded by new sources of energy. Before that, most energy was derived from wood. Some of it derived from coal, but on a very small scale. People used coal in a household setting. And they also might have used coal in a few small industrial enterprises like blacksmithing and that sort of thing. But it was not used on the industrial scale to which it became used in the Industrial Revolution. The Industrial Revolution was largely funded by coal. And coal is old, fossilized plant matter. It is very ancient, millions of years old, and it resulted from plants which formed large forests, especially in the Carboniferous era, becoming fossilized underground. And so it was a neutral store of carbon. Carbon on its own only reacts very, very, very slowly with oxygen, if at all. And it's so these huge stores of carbon were actually sequestering carbon away from the atmosphere. Later on in the Industrial Revolution, in the 19th century, oil was discovered as a fuel and energy source. And oil similarly is a fossil fuel. It is formed from the bodies of planktonic plants and animals, which become compressed, and their carbon is converted into these oils, which can be used as fuel. So they're also a fossil fuel store. And under normal circumstances, those oil reserves sequester carbon. They take it away from activity in the atmosphere. So we also need to just realize, I've talked a lot about carbon dioxide, and that's for a reason, because carbon dioxide is the most important of all of the greenhouse gases. And but there are other greenhouse gases as well. The most important, and it's becoming increasingly important in modern era, is this CH4 is methane gas. And methane gas occurs in huge stores underground. It also occurs locked into permafrost, which is permanently frozen ground at the high latitudes. And it also occurs in huge amounts on the sea floor, where it is actually frozen. Methane can be even without pressure, methane can be very easily liquefied, and just by lowering the temperature. And on the sea floor, it is actually frozen into huge stores. The other greenhouse gas also a product of industrial activity, and is nitrous oxide, N2O. Both of these actually are very powerful, even though they're lower in concentration. These are both very powerful greenhouse gases. And but of all of them, it is carbon dioxide that has resulted in the majority of our atmospheric warming, global warming. So we have to ask a question now. How do we know that for instance, those Mauna Loa curves that I showed you, and we'll see them again in a minute, how do we know that that is due to human activity? Could it not be natural occurring gases, increasing in the amount of gases, etc.? Certainly, there are sources of greenhouse gases apart from human activity. The most important would be gases from volcanic eruptions, for example, which belch a lot of carbon dioxide into the atmosphere. That is true. There's also variations in the sun's input of energy. As I hinted before, there are variations. Sometimes we receive more, and sometimes we receive less due to the variations in the orbiting of the Earth and the tilt of its axis, as you'll learn. But when we look at the last 200 years, neither of these can account for the increases in carbon dioxide levels that we observe. There are no natural occurring sources of carbon dioxide or other greenhouse gases which occur for the increases that we see. So this increase that we're watching here is due to human activity, and it can be relatively simply explained in this way. The carbon which is stored underground in fossil fuel stores, that is a store of energy. It was originally the sun's energy. It was originally fixed to carbon molecules by plants. As we've learned in our trophic pyramids and everything else, that energy and biomass can be passed up the trophic levels. But very often there was an excess of plant material which was not consumed, and an excess of planktonic material which died and was not consumed and went, especially settled out in oceans, and then was incorporated into sediments and formed oil. Plant material formed coal. And so what these fossilization processes were doing was it was taking carbon away from the possibility that it could function in contributing to carbon dioxide levels in the atmosphere. It was a store of carbon and energy. What we are doing now is we're accessing those stores, and we are liberating. We're doing it to access the energy that's locked into it. But in doing so, we are forced to actually convert that carbon into carbon dioxide. That is how we get the energy. Ultimately, we convert it to carbon dioxide, and that is a process which results in energy which we can use. And it is this industrial usage. When I say industrial, I don't only mean the factories, etc., etc. Our entire society runs on these sources of fuel. So our motor cars, our houses, our heating, everything runs on these sources of fuel. But what we're doing is we're accessing very ancient stores of carbon, and we are now converting it to carbon dioxide and pumping it into the atmosphere. So that's just a summary for you of that. Okay, so what is the impacts of these? Well, first of all, we have to realize that there has, in fact, been a prodigious increase in the overall global temperatures. And that applies to all areas of the Earth. Some areas it applies more than others, but all areas of the Earth have been subject to warming as the carbon dioxide levels and other greenhouse gases have increased in our atmosphere. These can have very, very grave impacts on human civilization, let alone on ecological structures. So the first thing that we need to worry about are things like agriculture. The agriculture depends, of course, on regimens of temperature and water access and everything else. As global temperatures rise, we are seeing increasing difficulties in growing crops in areas which has become subject to drought, where water accessibility falls, rainfall normal rainfall patterns are disturbed, and many areas are becoming extremely stressed, and unable any longer to reliably grow the crops that they did before. And the second thing is that water sources are affected, not only because rainfall patterns are disturbed, but there are aspects, for example, that as temperature rises, ice sheets, glaciers tend to melt, and this affects water availability. This also, by the way, affects global sea level. As land-based ice melts and flows down to rivers to the sea, it results in a rise in sea level. And this is a major threat to coastal habitation all around the world. Most of the world's population live very close to coasts. And as a result, global sea level rise is an increasing threat. As we hinted at the beginning, when I showed you the movie of the current storms in California, global heating actually destabilizes the normal climate patterns by pumping heat into areas which must then be redistributed. And so it destabilizes the atmosphere. And this leads to more frequent, stronger storms and instability in those cells, in those circulation cells, which we saw before. And so what we risk seeing of more frequent, stronger storms, more frequent and longer lasting droughts, heat waves, and everything like this. And we're going to see that this has a tremendous impact on human populations, and actually drives human migration as well. So in ecological terms, what is particularly damaging about these changes in climate is that they alter the structure and the location of biomes. So in fact, what will happen is the climate regimen in a biome will change and might be applied somewhere else. So for example, here is a prediction of the impacts of climate change on biomes, for example, the deciduous forest biomes, for example, of Pennsylvania or the East Coast. And in fact, the climate change will lead, it is predicted, to these becoming much more similar to those of Florida, as I showed you at the very beginning when I said, what would climate change look like? This is the risk that we run. This is this red, by the way, this is a prediction if we carry on burning carbon at the same rate as we are doing now. So if we carry on the same rate we're doing now, by 2099, Pennsylvania is going to begin to look like Florida. This yellow here is a lower usage of carbon, not a cessation of fossil fuel use, but a lowering of fossil fuel use. And the shift is much less, but it is still marked that Pennsylvania ends up looking much like Washington, D.C. or Virginia in that scenario. Now, look at the time spans that we're talking about, and you'll realize that these way less than 100 years. And we're affecting a massive change in the biome over a very short period of time. And it is highly unlikely that animals especially would be able to adapt to these kinds of changes. What you really risk seeing if animals are not able to move somewhere else to a biome that is shifted to their preferred biome structure, what we risk seeing is massive extinctions of different organisms, which we actually are already beginning to see. So I'm not going to go into details about this, this diagram. I just want to point out to you that these changes in biome structure and in seasonal structure actually begin to affect and are being seen to affect things like bird migrations. Now, birds migrate with a specific intent. They migrate to areas which are going to be best suited for them to breed in. And then in winter, they migrate away to an area where they can establish a maintenance diet and everything else, getting ready to migrate back to breed again the next season. There's a peculiar phenomenon in North America, and that is that in California, largely because of the types of storms that we're seeing right now, persisting late into the spring is actually being delayed on the West Coast. So spring is occurring later. On the East Coast, however, the opposite is true. Our spring, as you may have noticed, is coming earlier and earlier. And unfortunately, these migrations of birds are determined largely by day length. And day length doesn't change. Excuse me. So day length doesn't change. So the birds migrate under impulse to these areas, and the areas are not ready. In this case here, the season hasn't advanced enough for them. In this case here, the season has already proceeded and gone past what they need. So the breeding efficiency of these birds is substantially reduced. So just give me a second. Okay, so it's affecting migration, but the greatest risk in migration terms that we face in the future, it is already occurring to some extent, but here are predictions not far in the future. This is in 25 years or so. By 2050, these are the human migrations which are predicted will occur as a direct result of global climate change. And these are for a variety of reasons. The first is climate itself. Some areas are just going to become so hot, especially in summer, that people cannot survive there. The heat waves in India, Southeast Asia already are close to the limits that human beings can bear, and people are already moving away from areas that become too hot in winter and in summer, and where the summer persists too long. The second is agriculture is so radically affected. Water availability becomes affected. Crops can't be grown. People face famine, and they migrate to areas where farming would be easier, or where they have an alternative income and a source that they can use. So there are various pressures on human beings. Third one is the result of global sea rise, and that is due to melting of ice caps, glaciers, etc. And that is a movement away from low-lying coastal areas, especially island nations. And people are being forced already to migrate away from the areas which are being flooded. So here are the predictions, and they're quite drastic. South America, by 2050, 10.7% of the population is going to be forced to move. Sub-Saharan Africa, 71.1 million people. North Africa, 13 million people, etc. This is the startling one here, and that is 35.7 million people from India alone. And from the rest of East Asia and the Pacific, 36.2 million. Those two together equal almost to the movement in Africa. These are huge migrations, absolutely huge migrations. Just think about what is happening on the southern border of the United States at the moment. Those migrations are largely driven by politics, crime, etc. Those kinds of migrations will be dwarfed by the migrations which are forced onto human beings as they simply try to move somewhere where it's possible to live and make a living, because the areas where they live have become unlivable. So we've discussed a lot about land and about the impacts on land, what might happen, etc. But we also need to realize that the increase in carbon dioxide is not only in the atmosphere, it's in water as well. And about 50% of the carbon dioxide pumped into the atmosphere ends up being dissolved in water, the oceans and lakes and rivers, etc. So this has very, very profound effects on the ecology, particularly of marine systems. So as we dissolve carbon dioxide into water, it makes the water more acid. So here's a graph. This is our pH. You may or may not know, the lower the pH, the more acid the solution is. So as the dissolved carbon dioxide increases in ocean waters, so they become more and more acid. Now, this is not a huge difference, but for many, many, many millions of years, the pH of seawater has been relatively constant, and organisms in seawater have evolved to be adapted to that particular pH. And if we change the pH, it's going to result in very damaging situation for many marine organisms. So here we're watching increase in dissolved carbon dioxide and a decrease in pH. So this affects many, many marine organisms, particularly those which use calcium carbonate, chalk, basically, as a structure for shells, skeletons, etc. And so seashells, that is calcium carbonate. So corals are built of calcium carbonate. But even more important are things that you can't actually see. And these are planktonic organisms. Here a whole lot here. Often with very beautiful shells made of carbon dioxide, of calcium carbonate rather. And all of these organisms are going to find it increasingly difficult to actually make these shells and maintain them as the water becomes more acid. You don't need a big change in the pH to radically affect the ability of organisms to make and maintain a calcium carbonate skeleton. So all of these organisms are becoming extremely stressed by these increases in carbon dioxide and the decrease in the pH. So the coral reefs are under particular threat for a lot of reasons that I won't go into now. Coral reefs are actually relatively fragile ecosystems in many terms. And they exist in a very, very narrow range of temperature and pH, etc. So the first thing to explain to you is have a look here at these corals here. First of all, they are built around a skeleton of calcium carbonate. But there's a very, very thin layer of tissue. The animal itself is a very thin layer of tissue over this and embedded in the skeleton. The color here is due to organisms which live inside the flesh of the coral and which actually photosynthesize. And they live together with the corals. They are in symbiosis with the coral, and they contribute products of photosynthesis to the coral animal itself. It's an essential partnership in corals. And you can see these are healthy corals here. They have their symbionts living with them quite happily. But have a look here. This is what results when you warm coral reef too much. And these corals have expelled all of their, I won't want to call them algae, but their photosynthetic cells. They've expelled them. And so they lose their color. This is the phenomenon known as coral bleaching. And it's very, very dangerous. Sometimes they can recover, but other times they don't. And the coral will actually die. And many of them, the ability to recover is retarded if the temperature remains high. They require cooling in order to recover from and regain their photosynthetic cells. So that's the first thing. Coral bleaching results from warming. But acid seawater weakens these skeletons as well. And it's not only that established skeleton is weakened, but the coral finds it more and more difficult to grow. And realize that coral reefs are continually being battered by waves, continually breaking. They continually need to grow in order to replace what is eroded away by the wave action. And if they do not do so, the coral reef begins to collapse and be lost. So coral reefs get a double whammy. They get a double whammy from temperature and from the increasing ocean acidity. But our great worry in the oceans, I'm not going to go into the details of this. You learned something about, a little bit about ocean currents before when you talked about climate. But I do want to point out that there, overall around the whole world, there is a huge circulation system in which water over a period of thousands of years, by the way, moves all through. A single water molecule will move through all of the world's oceans in a huge and very complex current pattern. The current patterns all link with one another. And they are driven by temperature and by rainfall and by wind, surface wind. They're also driven by salinity, very importantly. And all of these things are affected by temperature, by atmospheric temperature. And there is a tremendous worry, for example, that ocean currents are going to be slowing down. And we are already, this current here is the Gulf Stream here. And this is of particular worry because Europe is warmed by the Gulf Stream. Europe is so high, in such high latitude, that it should be much colder than it actually is. It's kept warm by the fact that winds blow off the Gulf Stream and warm the whole of Europe, of Western Europe at least. And there is tremendous worry that the Gulf Stream in particular is actually showing signs of slowing down. This whole pattern here, driven by all of the different factors, salinity, rainfall, wind, etc., that driving force is weakening as the planet warms. And there's real concern about the impacts of changes in ocean currents that is going to result. Okay, so let's just have a look, just to point out where the global carbon dioxide is coming from. And I'll point out, first of all, China has been the greatest contributor to, in relative terms. But that is in fact changing because China has invested a huge amount of money in renewable energy resources, wind and solar. And there is hope that, in fact, this is going to decrease. Here is the United States. China contributes 28%. It's a huge amount. But don't forget, it's a very, very large country with a very big population. United States contributes 15%. And I'll point out to you that 15% is the same as all of these: Canada, Mexico, Brazil, Germany, France, United Kingdom, and these all added together. So we contribute a huge amount relative to our size. And that's because we are profoundly consumer society. We have not yet caught up to China in our renewables. Hopefully we will. But at the moment, we contribute a tremendous amount to the global carbon dioxide budget. So we have to ask what we need to do about it. And this is only a very, very, very brief introduction on this slide. The fact that this requires political will, and that political will has become expressed to a certain extent in a global climate treaty. This treaty is known as the Paris Accords, and the nations of the world under the auspices of the United Nations meet regularly to discuss the Paris Accords. They are commitments which nations have made to begin to limit their fossil fuel usage and to examine very carefully how much they are contributing to global warming, global heating. So here is, if you want to go there, here is a link to more information about the Paris Accords. The Paris Accords seeks to maintain global heating below 2 degrees Celsius, and that is about 3.6 degrees Fahrenheit. Our current heating is about 2 degrees Fahrenheit. So we're pretty close already. Our current heating since the Industrial Revolution really got going in the mid-19th century, we've heated about 2 degrees Fahrenheit or 1.1 degrees Celsius. And the Paris Accords strive very hard to keep heating below 2 degrees. 2 degrees Celsius is the level at which it is predicted that catastrophic changes will occur. So in actual fact, the last meeting, they actually realized that we are getting very, very close to the 2 degree. And there's now talk about trying to maintain the temperature less than 2.5 degrees. And the goalposts are being shifted. And the reason for that is that while nations will sign on to treaties, very, very few of them have met the goals that they set for themselves in limiting fossil fuel usage or in establishing renewable sources. So we have various scenarios. Here we are here just close to 2 degrees Fahrenheit. We're around about here. There are different scenarios. Here is the scenario for temperature change if we carry on exactly the way that we are doing at the moment. If we carry on our fossil fuel usage and as we have been doing, we continue to pump the same amounts of carbon dioxide into the atmosphere along with the other greenhouse gases. Here's the predicted temperature. 3 degrees Celsius is a level which most climate scientists do not even want to contemplate because the effects will be so disastrous. But here's the projected increases. There comes a point at which these simply become unlivable. Here is the modified. This is if nations modify their use of fossil fuels and carbon dioxide release. There is a modified which will maintain temperature below 4 degrees Fahrenheit of change. So this is less desirable, but more likely, given the commitment that nations have shown to changing their fossil fuel usage. And this here is the ideal. And this maintains the increase in temperature at just over 2 degrees Fahrenheit. And this requires massive changes in industry, in use of fossil fuels. This is almost a cessation of fossil fuel usage. So, in fact, I unfortunately think that this curve here is probably the more likely that we'll accede to. Okay, so I know it's not the most cheerful topic at the moment, but don't forget that huge changes can occur very, very rapidly, especially with new technology. And one of the new technologies that we really need to think about is that of carbon capture. And science is looking at efficient ways of actually taking carbon dioxide out of the atmosphere and turning it back into a neutral store of carbon. It's, in a way, developing a fossil source, a fossil reservoir, rather, of carbon extracted from the atmosphere. At the moment, it can only be done on a relatively small scale, but that is one real area of hope for the future. And you in your lifetimes hopefully are going to see massive changes in first of all, our attitude towards the planet, and second of all, in our profligate usage of fossil fuels, which is causing all the difficulties that we see now. Okay, so there are a number of exercises. Please look at all of the movies. I have put there on your schedule how long those movies take, and you'll see it's not very long at all. Please pay careful attention to the interactive exercise, especially. There is a student worksheet for you to fill out and to hand in with that. And then please contribute to the discussion groups and read what I've put there really carefully, so that you you contribute to the discussion groups according to what I have asked you to. Okay, and I will see you again next week.